Hi everyone. We're starting a new chapter, and in this chapter we're going to discuss ethers, epoxides, thiols, and sulfides. So here I tried to find some good representative pictures of each type of functional group. So on the upper left you can see we have an ether. So that has an oxygen in between two alkyl groups, and those alkyl groups might be the same or different. On the upper right, we have an example of an epoxide. So that has an oxygen in a ring system, and we've seen this previously when we used MCPBA in one of our reactions. Down below, we have a thiol, where sulfur is bonded to an alkyl group and a hydrogen. And finally, sulfides, which contain the sulfide ion, and this has a -2 charge. So typically sulfides are found with metal ions. Now we're going to start first with ethers, and then later we'll move on to epoxides, and then even later we'll talk about thiols and sulfides. So let's start with ethers, and your textbook gives some good examples of where you can find ethers in pharmaceuticals. So for instance, in the compound for morphine, you can see we have an ether functional group. And morphine is mostly used as a pain reliever, although you can get addicted to it. So the other one I wanted to show was propanolol, which is used for blood pressure. So there's an ether group there as well. And down below we have a structure for vitamin E, which is really good for your skin. So that has an ether group as well. Now, of course, these pharmaceutical drugs, they have other functional groups in them as well, but these are just examples of ethers, so we're just focusing on those for now. Now, let's talk about how to name ethers. So earlier I mentioned that ethers have an oxygen in between two alkyl groups, and those alkyl groups could be the same or different. So let's look at a couple of examples. All right, so we've got this one where we have two ethyl groups on either side of that oxygen. Maybe we have one where there's an ethyl group on one side, but a methyl group on the other. And maybe we have an ether where on one side we have a methyl group, and then on the other side we have a tert-butyl group. All right, so how do we name these? Well, we just start by identifying the groups on either side. So for instance, in our first ether, we have an ethyl group on each side. So we would call this diethyl ether. And this is actually a really good solvent. So we use this a lot in organic chemistry. Now looking at the next one, we have an ethyl group and a methyl group. So this one we would call ethyl methyl ether, and remember to alphabetize the substituents. So ethyl methyl ether. And then in the last one, we said that we had a tert-butyl group and a methyl group. So this one would be called tert-butyl methyl ether. Now, remember when you're alphabetizing, we don't include the tert part, so we just consider the B on butyl and the M on methyl. Okay, so notice that if the alkyl groups are different, we list each of those groups, but if the groups are the same, then we put, for instance, di in front of the group. Okay, so now let's talk about some physical properties of ethers. So ethers do have an electronegative oxygen. So let's say we have this particular ether here. And let's say that we have a water molecule nearby. Actually, let me redraw that. The oxygen from the ether will be attracted to the hydrogen from water, and they will form a hydrogen bond. So it is possible to have hydrogen bonding between an ether and a molecule that does have a hydrogen either bonded to fluorine, oxygen, or nitrogen. So remember that term, hold the phone, FON. Now, what if we just had ether? So what if we just had a bunch of ethyl, methyl, ether? Is there any hydrogen bonding between those? No. What kind of intermolecular force would exist between two ether molecules? Would we have van der Waals forces? Would we have dipole-dipole interactions? Both, right? Remember, every molecule has van der Waals forces or London dispersion forces. Sometimes we use a different name for that. But we would also have dipole-dipole interactions because that oxygen is so electronegative compared to the carbons and the hydrogens on the alkyl groups. And additionally, remember that we could have some van der Waals forces between the carbons on either end as well. And I'll write underneath dispersion. Okay, so now let's talk about boiling points of ethers. So what if we just have a really simple ether like dimethyl ether? And let's compare that to diethyl ether. And then we'll compare that to dipropyl ether. So we're just kind of adding on to the carbon chain on each side. So this is dimethyl ether on the left, diethyl ether in the middle, and dipropyl ether on the right. Which one do you think has the highest boiling point and why? So you might recall that even though dispersion forces are really weak, if you have a lot of dispersion forces kind of adding up together, then that can create an overall really strong bond. So in Chem 261, we talked about geckos and their feet and how their feet have little hairs on them. And those hairs have dispersion forces. So they can crawl up walls and on ceilings, etc., because they have so many hairs on their feet that have dispersion forces. So if you have a bunch of dispersion forces, you can have a pretty strong interaction. So the more carbons and hydrogens we have on our ether, the stronger the force between molecules. So for instance, if we draw another set of each molecule here, we can kind of see that the dispersion forces are going to increase the more carbons we have. So the interactions get stronger the more carbons we have. So dipropyl ether has a boiling point of 91 degrees Celsius. Diethyl ether has a boiling point of 35 degrees Celsius. And dimethyl ether has a boiling point of negative 25 degrees Celsius. So you can see the more carbons we have, the more interactions there are between the molecules, and the harder it is to break them apart. You need more and more heat in order to do that. All right, now let's talk about some common ethers. So we've already talked about one of them. Diethyl ether is one of the most common ethers. Another name for this ether is ethoxyethane. So the ethoxy comes from the alkoxide group that could form. And then ethane refers to the 2-carbon chain on the other side. So just a different way of naming the same molecule because, we just have to make it super confusing for everyone. All right, so diethyl ether, again, is a really good solvent. All right, and then another common ether is called tetrahydrofuran, and we've seen this one before. So remember when we're performing hydroboration oxidation, we connect a borane molecule to tetrahydrofuran in order to limit the diborane molecules. So this is tetrahydrofuran, or THF. So this is also a really good solvent. And remember too, like we just said, it can form a complex with a boron-containing molecule. And then the last one, let's see if I can squeeze it in here at the bottom. This one's called 1,4-dioxane. So this one has a higher boiling point than diethyl ether, which makes it more useful for reactions that have or need a higher temperature in order to occur. All right. So let's talk about some uses of ethers, and we've already kind of covered some of them, but we'll just summarize it on the next slide. So again, ethers are common solvents. Now, part of the reason that they're really good solvents is due to the fact that they're pretty unreactive. So we would say that they're inert. Additionally, they're good hydrogen bond acceptors, as we talked about earlier. Although they're not H-bond donors because they don't have a hydrogen attached. So let's just draw a little picture of an ether and some water. And then additionally, They're weak Lewis bases. So they can donate electrons to something that needs an electron. So for instance, we talked about borane bonding to tetrahydrofuran. And again, boron has an empty p orbital, so that allows the Lewis base to donate electrons, and then boron accepts those electrons. And then we end up with a complex between boron and the Lewis base. All right. Now, there's one other type of ether that we should talk about, and this is a really interesting type of ether. So this type of ether is called a crown ether, and these are really cool. So crown ethers look like crowns. So basically, you have a certain number of oxygens, and then they're all connected by a certain number of carbons. So this one I'm drawing, for instance, is connected by 2 carbon chains. And each of these types of crown ethers can hold a metal inside of them. So the first one here that I drew is called 12 crown 4. And this one can hold, excuse me, a lithium ion. So the oxygens are all electronegative, and they're all attracted to this positively charged metal. So they kind of hold the metal inside. Now, 12 crown 4 is small, so it really can only hold lithium, but there are other crown ethers that can hold larger metal ions. So the next one we'll draw has 5 oxygens, and they're all again connected by 2 carbon chains. And this one's a little bit bigger. It's called 15 crown 5, and this one can hold a sodium ion. So remember, as we go down a column on the periodic table, atoms get bigger and bigger. So sodium's bigger than lithium because it's lower down on the column. And then the last crown ether we'll show is called 18 crown 6. So this one has 6 oxygens. And then they're all connected by 2 carbon chains again. This one can hold potassium because potassium's bigger than sodium or lithium. Now, what's really great about crown ethers is that they can deliver an ion somewhere in a system, like in your body. So they can be used in medicine and other areas as well. So one useful thing about crown ethers is, let's say that you want to replace a bromine in an alkyl halide with fluorine. So maybe you would think, oh, what if I use potassium fluoride? So that fluoride is a good nucleophile and can substitute itself in. Well, like we've said in the past, fluorine is very reactive and it violently reacts. So it's pretty difficult to use it in different reactions. But one method that we could use instead, we could deliver fluoride using a crown ether. like 18 crown 6. So 18 crown 6 will grab onto the potassium ion, and that will leave the fluoride ion available to attack or perform a substitution reaction. And it should prevent it from reacting with anything else. Okay, so again, just a special type of um, ether, and this is actually also called host-guest chemistry. So you've got your host, the crown ether, you've got your guest, the metal ion, and it's all chemistry. All right, so I think we'll stop there today. Next time we'll talk about how to create ethers or how to prepare ethers. And we'll also talk about some reactions that ethers can perform. So I will see you then.